Hello everyone. So we're going to continue to talk about inferences for the rest of the semester. So you need to understand what inference is. We have generally two different types of inference. Either a conflict interval, when you try to estimate a measure of the population, basically a population parameter, as well as hypothesis test, in which you're trying to assess a claim being true or false about the population. So learning objective, we need to understand the relationship between Z statistic and T statistic. They're very much closely related. And the T statistic will have a T distribution. And the T distribution has another parameter called degrees of freedom. Okay? So we need to understand what degrees of freedom is, how do we find it, and how will the degree of freedom affect the density curve of the T distribution. And then T inference is a lot more useful than Z inference in practice. We're going to talk about the reason very quickly. So we need to be able to use T inference to solve any practical problem, basically either a T conflict interval or T test. Anytime you talk about the inference, it will be either conflict interval or test, we just talked about. And then lastly, anytime you do a T test, any hypothesis test, you need to use the 5-step procedure. So get familiar with the 5-step procedure we learned in chapter 15 and understand what each step is doing. That will be very, very helpful. So chapter 18, we're going to talk about the inferences about one population mean, but we're going to use a T inference. Okay. So in chapter 15, we used Z inference, involves Z conflict interval and a Z test. And in either case, we need to require to know a population standard deviation sigma. But population standard deviation is a parameter. We almost never know what a population parameter is, including population standard deviation. So this number is unknown most of the time. Then that will make Z inference not practically useful because the Z inference will require something we almost never know. So we're not able to do Z inferences, right? Then what do I do? So here's what do. We create a similar statistic so that we can bypass knowing standard deviation sigma and then do the similar inferences like what we did before. Okay? So we introduce the concept of T inference. Okay? So from last class or from central limit theorem, we understand from central limit theorem, X bar is going to follow a normal distribution. And normal distribution has two parameters, mu and sigma. So mu will be the same as original population. Sigma will be original standard deviation divided by square root of sample size n. Right? So then this is X bar has a normal distribution with the parameters mean and the standard deviation given. We know for any normal variable, we can always standardize that normal variable into a Z. Right? Z is going to be normal with mean equal to 0 and sigma equal to 1. Its transformation will be Z equal to X bar minus mu of X bar and then divided by sigma X bar basically, right? So where this will be mu of X bar and this will be sigma of X bar. Then from here, we know if we use X bar minus mu divided by sigma over square root of n, this is the definition of Z, right? And this is the Z, it will have a normal distribution with mean equal to 0 and standard deviation is equal to 1, right? And this will be the z score we use in z inference. So this is from the last two chapters. So when you look at the definition of the z statistic, the only problem we have is the sigma. Sigma is most of the time unknown to us. If we don't know what that sigma is, we're not able to compute z. We can't define z that way, right? So we can't calculate the z that way, then this is not useful. So if you're able to find something to replace that sigma, then we can define a different statistic. So for example, if we keep everything else exactly the same, but we're going to replace sigma by something else. Sigma is population standard deviation. What is the best estimator do we have that we can calculate from a sample that is close to population standard deviation? The best alternative will be sample standard deviation S. Right? So if we define x bar minus mu divided by S over square root of n, this is no longer a z statistic anymore. We define this as a new statistic. This is a t statistic. Okay. So a t statistic will follow a t distribution, and the t distribution will have a parameter of a degrees of freedom. Okay. But the t distribution and the z distribution, they are very similar if you draw the density curve. So z distribution, symmetric, bell-shaped, center is 0, standard deviation is 1. T distribution, symmetric, bell-shaped, center is 0, but the standard deviation is going to vary depending on the degree of freedom. Okay. So we only have a unique z distribution, but t distribution, we have many different t distributions. Okay. But all the t distribution will be symmetric, bell-shaped, center at 0. Okay. Then if we have a t distribution, then we can use t-statistic to do inference. We can do t-inference. And in this case, we no longer need to know what the population standard deviation anymore if we choose to do t-inference. Okay. So then, how do we know what degree of freedom do we have for each problem? For one sample problem, degrees of freedom will equal to sample size n subtract 1. Okay. Then when you have a different degrees of freedom, you're going to have a different t distribution. And then we're going to need to have a t table to show us what the t distribution look like for each different degrees of freedom. Okay. And then another thing is we need to introduce another term. So we know sigma over square root of n. This term is called standard deviation of sample mean x bar. Okay. So sometimes we use standard deviation of x bar represent. That will be sigma over square root of n. Then if we replace that sigma by s, this is just like a standard deviation, right? But we can't call this standard deviation anymore because that term is already used. So we just need to give a different name. This is called standard error of sum of in X bar. So we use STDERR, standard error of X bar, or equal to S over square root of n. So anytime if you see a standard error of X bar, don't get confused. Applying central limit theorem, basically replace that sigma by S. That's what a standard error represents. Okay. Right. So I talked about T and Z distribution very similar, right? So this is our Z definition. X bar minus mu divided by sigma over square root of n. And this is our T definition, simply replacing that sigma by S. We have a unique Z distribution. The Z distribution will be symmetric, bell-shaped, center at 0. So this is the black line here is basically our Z distribution. And then we have many different T distributions. The T distributions we have here, the orange line is degree of freedom equal to 1, and purple line degree of freedom equal to 2, and then the blue line degree of freedom equal to 5. But it could have other degree of freedom as well. It can have degree of freedom equal to any number. Okay? So you have infinite number of T distributions between here and here. You know, you can draw many different T distributions. So you can see the similarities between Z and T. They're all symmetric, bell-shaped, center at 0. Right? And then for T distribution with different degrees of freedom, we can see the distribution is very similar, but we still are able to see the trend, right? When the degree of freedom increases, the distribution will get closer and closer to Z distribution, right? So when the degree of freedom goes to infinity, it will just become Z distribution. And that you can also think about a scenario. You know, when you think about the definition difference between Z and T, that does make sense. So basically, if you have a population here, and you take a sample out, sample size equal to n, right? Then the Z statistic is X bar minus mu divided by sigma over square root of n, where T statistic is X bar minus mu divided by S over square root of n. Then, for the T distribution, degree of freedom equal to sample size n minus 1. If the degree of freedom goes to infinity, that means the sample size will go to infinity as well, right? So what does it mean then? That means the sample will take all the individuals from the population, right? So n will be infinity. You're gonna replicate the whole population in that case, right? If this sample become your population, then the standard deviation of the sample will become standard deviation of the population, right? So in that case, Z and T will be exactly the same when S is sigma, right? So that's what they're saying. When the degree of freedom for T distribution goes to infinity, the T distribution will just be the same as the Z distribution, right? So now we know what the T distribution is. How do we use T statistic to do the inferences we learned in chapter 14 and 15 for the confidence interval or hypothesis test? So here's what we do. So this is a T distribution table. We're going to go back here. to learn about how to use it. The first animal for this lecture is a line. All right. So we have two different kind of inferences. One is confidence interval, the other is hypothesis test. So we're going to start with confidence interval. Okay. If you think about Z confidence interval, we use X bar plus or minus Z star times sigma over square root of A, right? So we can do a similar transformation from Z to T by changing the Z star into T star and change sigma into S. Then this will be the process of calculating T confidence interval. Okay? So in the T confidence interval, X bar, that's sample mean, N, sample size, S, is sample standard deviation. They're all sample statistics. We're able to find all of the sample statistics. They're known to us. We can calculate them. And then the question will be, basically, as long as we know what T star value we can use, then we can do the calculations. Right? So where do I get T star? Just like, you need to get a Z star from Z table, right? So T star is going to come from a T table. Okay? And the degree of freedom for one sample problem will be sample size N minus 1. Okay? Now let's look at how do we look up on the T table. So if you have your T table on hand, the T table will give you degree of freedom on the first column from 1, 2, 3, 4, 5 up to Z star just indicate degree of freedom because it's infinite large. And the T table is designed just for the use of t-inference, either confidence interval or hypothesis test. It doesn't give us as much detailed information as Z table. Another reason is in T table, we give many different distributions. Every different degree of freedom has a different T distribution. So basically, you only have one line indicating one T distribution. If you look at different row, there's a different T distribution. So every time you use the T table, you're supposed to only look at one single row for whatever your degree of freedom is. So check your degree of freedom first before you use the T table. Okay. So the left column is your degree of freedom, and then the bottom is your confidence level. Okay? And the top is the upper tail probability. And all the values inside are t-scores. Okay, so all the values inside are t-scores. So the design of the t-table is different from the z-table. We need to make sure we use the table, appropriately. So then how do we find t-star? So t-star will be just one of the score inside the table. They're all t-scores inside, right? How do I identify? The process is very simple. So for any problem you work with, identify the degree of freedom you have. So if your sample size is 10, degree of freedom will be 9. If your sample size is 100, degree of freedom will be 99, right? And also, the confidence level is given on the bottom. You have 50%, 60%, 70%, 80%, 90%, 95, 96, 98, 99, 99.5, and so on, right? So then, when you do a confidence interval, you need to decide what confidence level to use. In the class, I will tell you what confidence level to use, right? But the default is 95% if it's not given. So you know what the confidence level to use, you know what degree of freedom to use, then we can find, we can use the t-table to find the t-score appropriately, right? And then once you are able to find the t-score, then we're able to calculate. The same deal as the z-confidence interval. Basically, you have two numbers calculated, small number on the left and a large number on the right. That will be how you write the confidence intervals format, and then write a conclusion, the same type of conclusion. We have C% confidence that the population mean is between this number and that number, right? So that's how we do t confidence interval. And also the margin of error we learned in z confidence interval. The last term, that's margin of error, right? So basically, anytime you have a confidence interval calculated, X bar will be right in the middle. And on both sides, you basically either add or subtract our margin of error, right? In the z confidence interval, the same deal. So the part after the add and subtract sign is your margin of error. Okay? And you always want to have a smaller margin of error so that your confidence interval will be narrower, right? Because the confidence interval is always twice as large as your margin of error. All right. So then, how do we control the margin of error here? The same idea. So t star as and the square root of n, when it goes through that, the best option is make sure to increase your sample size. Once you increase your sample size, you can get a smaller margin error. Then you have a smaller, narrower confidence interval. So what are the conditions for using t-inference, both t-confidence interval and t-test? It's basically just taking out the last condition of the z-inference. So in this case, we no longer need to know the population standard deviation anymore. And that's what makes t-inference a lot more useful in practice. So all we need to do is, all we need to have is, we need to have a random sample, as well as we need to have big sample size to apply central limit. Right. So like I mentioned earlier, the critical thing in t-confidence interval is how do we find the t star level, right? Okay, so we're going to practice real quick. How do we find different t star level for different problem here? So for example, in first, we have 90% confidence level when the sample size is 10. So then, very easy. The degree of freedom will be sample size n minus 1, which is 9. And then confidence level is 90%. So what t star should we use? If you go back to the table, confidence level 90%, degree of freedom equal to 9. So you find the cross section inside the table, that will be the t star to use. 1.833. Right. And likewise, you can easily find, t star values for any other examples, right? So let's quickly find it. For example, with 95% confidence level and sample size is 8, that means degree of freedom equal to 8 minus 1 equal to 7, and the confidence level is 95%. So we can find the t star as 2.365. And number 3, a 99% confidence level with degree of freedom is 25 minus 1 is 24. So we got 2.797. And so on, right? And also in t-table, just like in z-table, you have a continuous distribution. There's no way the table can give you all the possible values of the t-score or all the possible values of probability or confidence level. So we need to approximate if needed. Right? So for example, if your sample size is n is 100 and your confidence level is, for example, 91%, then what t-star do I use? So then you need to know the degree of freedom will be 99, right? Then you go to t-table, you realize, hey, there's no degree of freedom 99 there, right? But what is the closest degree of freedom? Approximated using 100, right? And they don't have confidence level 91%, right? And what is the closest confidence level you have? 90%, right? You can approximate it. Okay. So in that case, t-star will be 1.660, right? And once you're able to find t-star, then basically the t-confidence interval is done. You can do the calculations just like what you did in z-confidence interval, right? X bar plus or minus t star times s over square root of n, plug in all the numbers, and that's it. Okay? So let's work on the practice. A study of longleaf pine trees is conducted. There are 865 trees in the population, and 40 trees are randomly selected in the sample. Their diameter at breast height, that's the verb of interest, are measured, and the mean and standard deviation of the sample is 27.29 and 17.71 respectively. So basically, the first number is the mean of the sample, which is x bar. The second number is the standard deviation of the sample, which is s. Right? And then, first question, draw a histogram about the data, starting with 0 and with a width of 5. So you can make a histogram. We're gonna look at it very quickly. So, this is, what a histogram look like for DBH. Most of the time, we examine the histogram of the sample just to so that to see, hey, what is the distribution of the population we're interested in? Is it close to normal distribution? Is it, discrete or continuous? Is it skewed or symmetric? And then basically, how large does the sample size need to be if we want to apply central limit theorem? We just want to make sure central limit theorem will be able to apply. Okay. So when you look at the distribution, even though it's not, it doesn't look like normal, but this is a continuous variable, right? As well as this is not as, skewed, right? So sample size of 40 is not too bad to apply central limit theorem. And once central limit theorem applies, then we know we are able to use, t-inferences, right? And we evaluate the distribution of data close to normality. We just talked about it. And then lastly, suppose the sample size is large enough to use the t-confidence interval, basically large enough to apply the central limit theorem. What can you conclude on the average DBH for all the pine trees in the study at a 95% confidence level? So basically, these average 27.29, that's only the average of 40 trees in the study you selected as a sample. Then what do we know of the average DBH for all the trees in the study, right? So what's the average of the population? So we need to estimate it. And how do we estimate? We're going to need to use a confidence interval, right? Because we're doing estimations, so this is a confidence interval. And now, if you look at the question, the standard deviation is nowhere to be given for the population, right? Sigma is unknown. We're given S, but we don't know sigma, right? If sigma is unknown, we need to know we can do Z process anymore, but we can do T process, right? So we need to do a T confidence interval. That's because sigma is not given. Then for T confidence interval, the formula is easy, x bar plus or minus P star times S over square root of n. You don't need to memorize the formula. The formula will be always given for, all the processes. Then, same deal, we need to calculate. So we need to find each of the numbers here. We need to find x bar, we need to find P star, we need to find S, and then we need to find n. Okay? So in the problem, we're given x bar and S, which is 27.29 is x bar, 17.71 is x. So we're going to put them here, 27.29, and then S is 17.71, I believe, right? 17.71. Then n is sample size. So if you look at a problem, what is sample size? We have 40 trees as our sample. So that means the sample size will be 40, right? So this is our n. Then the last thing we need is T star, right? So T star is related to two things, and we can look it up from T table. One is degrees of freedom, which is sample size n minus 1. So 40 minus 1, that will be 39. The other will be confidence level. In this case, we're needing to use 95%, right? So then when you go to T table, 95%, and degree of freedom is 39. The closest on the T table is 40, right? So then T star is 2.021, you approximate it. Then the rest is math. You plug in the numbers, do the calculation, x bar, plus and minus P star times S over square root of n. And then you need to do an addition calculation, you do a subtraction calculation, right? You can have two numbers. So for example, with the subtraction sign, we calculate number to be 21.6. And the big numbers, the addition sign, you're going to calculate number 32.9. Then our confidence interval calculated to be 21.6 and 32.9. And don't forget, any difference, I will require you to write the interpretation, the conclusion, right? It's the same format. We have C% confidence, so we have 95% confidence that the population mean, average of the population, the average DBH of all pine trees in a study is between 21.6 in the unit, if you can put a unit here, and 32.9. So that concludes, T confidence interval. So you have the complete process over here. All right. And the second animal for the attendance points is panda. All right, let's look at another practice. The composition of the Earth's atmosphere may have changed over time. To discover the nature of the atmosphere a long time ago, we can examine the gas in bubbles inside the answer number amber is a tree ration and is hardened and been trapped in rocks. The gas in the bubbles within the amber should be a sample of the atmosphere at the time when the amber was formed. Some specimen of the amber from late Cretaceous era, very long time ago, give us the percentage of nitrogen as the following. So we have different nitrogen percentage based on the amber sample we collected. Suppose these observations are a simple random sample from late Cretaceous era, and the nitrogen percentage in the amber has a normal distribution. Use a 90% confidence interval to estimate the percent of nitrogen in ancient air. Okay, so you need to analyze the question first. So we are doing an estimation. That means we need to do a confidence interval, right? Then, is there sigma given? Of course not, right? Sigma is unknown. And we can't calculate sigma, right? Then this will be a t confidence interval, right? So it's always, the first step is determine what the inference procedure to use, okay? So this will be a t confidence interval after you read the question. Then we're going to have x bar plus and minus p star times s over square root of n, right? So that's the process we need to work with. Then we need to find what is x bar, what is t star, what is s, and what is n, right? So let's work from the easy ones. What is n? N is sample size. And it's clearly that we have, I think it mentioned here, well, I didn't say how many ambers are there, but we can count at least, right? So 1 amber, 2, 3, 4, 5, 6, 7, 8, and 9, right? So sample size n equal to 9, right? You have 9 samples. And then what is confidence level? C% is our confidence level. So then based on this, we can see that sample size is 9. Then T star is related to 2 things. One is confidence level. We know that's 90%. The other is degree of freedom. That's n minus 1. 9 minus 1 is 8, right? So we can look up the Z table. We can look up the T table. So 90% confidence level, 8 degree of freedom. The T star we need to use will be 1.86. Right? Then, as well as we need to find sample mean and sample standard deviation. And I hope you guys still remember how to find the mean and standard deviation from a long time ago, from chapter 2, right? When you have any variable x, you work on the table, right? You can get a total here. This total will be summation of x. And then x bar will be sample mean. That's summation of xi divided by n, right? So you can calculate x bar. Then you can calculate xi minus x bar. Then you can find xi minus x bar squared. So once you have the whole table filled up, you can calculate the column total here. And this column total will be summation of xi minus x bar squared. And then your sample standard deviation will be square root of xi minus x bar squared divided by n minus 1. So that will go in there, right? So I'm going to skip the calculation. If you struggle with finding mean and standard deviation, refer to your homework number 1 for chapter 2. You know, we talked about how to find sample mean, sample standard deviation, right? So the mean will be 59.6. And the standard deviation will be 6.26, right? So then we have everything we need to do the calculation here. We plug in numbers, 59.6 plus or minus T star 1.860 times S, 6.26, divided by square root of n is 9. And then with addition and subtraction, we can calculate two numbers. With subtraction, we can calculate 55.7. And with addition, we can calculate 63.5. So the common interval we calculate will be between 55.7 and 63.5. And don't forget to write a conclusion as required. So we're going to say we have 90% confidence that the average nitrogen percentage in late Cretaceous era is between 55.7% and 63.5%. So this is T confidence interval. You can see it's very similar to Z confidence interval. The only difference is we need to change sigma into S, and we change Z into T, and T will come from a T table. Okay. All right, so this is T confidence interval. Then how do we do t-test? Okay. Think about for any hypothesis test, we talked about last class, that any hypothesis test, we need to go through the 5-step procedure. First step, state hypothesis. Second step, state rejection rule. Step 3, calculate test statistic and find p-value. You can refer to the chapter 15 for the procedure as well. Step 4, apply rejection rule to make a decision. And the last step is writing an interpretation by the conclusion. Okay. So when you go through the 5-step process, the only step being different in different hypothesis tests is only step 3. So in different tests, everything else is exactly the same. The only step being different is you need to calculate a different test statistic. So in z-test, you calculate the z-statistic. In t-test, you calculate the t-statistic. In f-test, you calculate the f-statistic. In chi-square test, you calculate the chi-square statistic. So you have a different statistic to work with this. And then p-value will come from a different distribution. So when you do a z-test, the p-value will be a probability from z distribution. You look it up from z table. Then in t-test, the p-value will be a probability in t distribution, which you need to look up from t table. Okay. And then everything else will be exactly the same as, z-test. Right. So then in t-test, how do we calculate test statistic? How do we find p-value? So it's very similar to z-test. So this is how we calculate test statistic, just the t definition. Compared to z statistic calculation, again, you can see the only difference is we replace that sigma by s, right? Once you replace that sigma by s, your z becomes t. Okay? So this is your calculated t. Then the p-value will depend on your alternative hypothesis, just like in z-test. When your alternative hypothesis has different signs, your p-value will be a probability of different event. But these are in terms of t event, right? So we need to look this up from t-table for the probability. And in terms of the one-tail, two-tail test is exactly the same because t-distribution is very similar to z-distribution. For the top two, we have a greater than sign or smaller than sign on the alternative hypothesis. These are called one-tail tests. And then when you have two unequal to alternative hypothesis, this will be a two-tail test. So we call it one-tail, two-tail test. Just basically look at if the probability of the p-value come from one side of the tail or two sides of the tail, right? So that's what one-tail, two-tail test is. So now the big thing is, how do we look up the probability from t-table? Okay. So now let's quickly look at the t-table design now. Right? So the t-table, all the t-score is in the table, right? The probability, only a few discrete numbers. We have 0.25, 0.20, 0.15. So only this top line is your probability. And then the degree of freedom will be indicating what t-distribution you're looking at, right? So for any time when you look at a t-distribution, for any degree of freedom, you can have a one-to-one match between a t-score and a probability, right? So for example, if you look at degree of freedom equal to 9, then the first t-score will be 0.703. The matching probability will be 0.25. And the second t-score will be 0.883. The matching probability will be 0.20, right? So for any t-distribution, for every single degree of freedom line, you have a one-to-one match between t-score and the probability. And what is that relationship? That relationship is indicated by the top density curve. Okay? So let's look at the process, the reasoning here. So for example, we just look at degree of freedom equal to 9. We have a one-to-one match between t-score and probability. So then, if the t-score equal to 0.703, the matching probability will be 0.25. And then, what is the relationship? That's indicated by the density curve on top. You have a t-distribution, center at 0, bell-shaped symmetric. So then, if the t-score equal to 0.703, then the probability to the right of the t-distribution is 0.25, right? That's the relationship we have. Then, this is, we're using density curve to show the relationship. Then we need to write it in a mathematical term. That means the probability of that area equal to 0.25. And how do we represent an area? That will be t greater than the score of 0.703, right? To the right of 0.703. Then for any other point, basically you have pretty much the similar relationship. For example, the next t-score is 0.833, 0.883. And then the corresponding probability is 0.20. That means we have probability of t greater than 0.883 or equal to 0.20. And that's it. You can have many similar relationships just like this. Okay? But then how do we use the t-table to find a probability? For example, if you want to find a probability of t greater than 0.81. How do I find that relation? How do I find that probability from the t-table? All right, so here we need to talk about the t-distribution in general. The t-distribution, symmetric, bell-shaped, center at 0. Right? So first thing I can ask you, if I have probability of t greater than 0, can you tell me what that probability will be? So to the right of t equal to 0, right? Then it's obvious that probability is 0.5. It's 1/2 the whole distribution. Right? The whole distribution has to be 1. Then probability of t greater than -1 compared to 0.5. So -1 will be on the left-hand side, right? Greater than -1 will be to the right of -1, right? Compared to 0.5, which one's bigger? Obviously, from here to the right is 0.5. This will be more than 5, right? So this will be greater than 0.5. And next thing is probability of t greater than 1 compared to probability of t greater than 2, which will have a bigger probability. So if you draw the line for 1, you draw the line for 2, 2 will be to the right of 1, right? Which one will have bigger probability? If you understand the area, greater than 2 will be the area on this tail, right? Greater than 1 will be the area in this tail, right? So obviously, this will be greater than that, right? Now lastly, between probability of greater than t greater than 1 versus probability of t smaller than -1, which probability is bigger? So here, greater than 1 from 1 to the right, smaller than -1 from -1 to the left, right? We know t distribution is symmetric, which means the two probability will be the same because the two area are mirror image of each other. Okay? So then if we understand the simple facts here for the t distribution, now we're able to find probability of t event. So for example, how do I find probability of t greater than 0.81? So we're still going to talk about the same degree of freedom. Okay? You have to know your distribution, what degree of freedom you have first. Okay? So if you look at the t-table, of course you're not able to find 0.81 in the t-table, but we're able to find the neighbors, right? We can compare the probability that we're interested in with the neighbor probability on the t-table. So for example, we can have two neighbors. One is 0.703, the other is 0.883, right? Then, if we compare probability of t greater than 0.81 with probability of t greater than 0.703, which probability will be bigger? We're going to use this rule, right? The bigger t-score will have a smaller right tail probability, right? The bigger the t-score is, means you're cutting on the right tail will be a smaller tail, right? So it's obvious it will be smaller than that, right? And what is that probability from the t-table? That's 0.25. And then if you compare the probability you're interested in now with the other neighbor, again, the bigger t-score will have a smaller probability, so this will be bigger than that, right? Smaller t-score will have a bigger upper tail probability. And what is this probability? 0.20, right? So if you combine these two together, we can see that the probability of t greater than 0.81, it needs to be greater than 0.20. At the same time, it needs to be less than 0.25. So you can write this as in between 0.20 and 0.25. And this is what we can find. This is how we find probability of t. So we're not able to find exact value of that probability like a z-table, but we're able to find a range. And the whole purpose of finding p-value is to compare with alpha. For example, if alpha is 0.05 and the p-value is between 0.20 and 0.25, we can easily see that p is greater than alpha, and we can conclude with failed to reject the null. And that's all we need to find the p-value. Right? So then, on the t-table, for any t-score that you have, you will only have 3 scenarios. So for example, if we're talking about degree of freedom equal to 9, one scenario is just like this. The t-score is going to be in between 2 numbers on the t-table. Then the probability of that with a greater than sign will in between the 2 probability of the 2 neighbor t-scores. That's one scenario. What if you're trying to find a probability of t greater than, for example, 0.5? So basically, this t-score is even smaller than any number t-score on the degree of freedom 9, right? In that case, you only have one neighbor. Just compare with that one neighbor. That will be 0.703, right? Then it's obvious, smaller t-score will give you a bigger probability, and this probability is 0.25. We can say that probability of t greater than 0.5 will be greater than 0.25. And likewise, you could have a very, very big t-score, for example, t greater than 6, with 9 degree of freedom, right? Then when you look through the t-table, it's all the way to the back. That means you only have one neighbor as well. Just compare with that one neighbor, which is 9 degree of freedom 4.781. Then the smaller t-score will have a bigger probability when you look at the right tails, right? So then this probability is 0.0005 from t-table. Then we can conclude the probability of t greater than 6 will be smaller than 0.0005, right? So that's all 3 scenarios that you could encounter when you look up t-table. But the most important thing is the t-table gives you right tail probability, right? That means before you look up the t-table, you need to make sure the sign is greater than sign. It's opposite from z-table, right? Z-table is the left-hand side tail, so you need to have a smaller than sign. T-table is right-hand side tail, so you need to have a greater than sign. All right, so we're gonna stop here. We're gonna continue next class to finish up the one sample t-test. Basically, the big deal is basically how do we use the t-table? Either to find a t-star value for confidence interval or find a p-value in hypothesis test. All right. Thank you, and let me know if there are any questions.